Hey guys, it's Mr. Lowry. This is the imaginary and complex numbers homework. This is the homework assignment that came from November 4th if you are in cohort A and November 5th if you are in cohort B. I wanted to give you some help on each one of these sections to get you started. Now in class we watched a couple videos and we talked about, imaginary numbers a little bit. But one of the things that we talked about that's going to be important for this assignment is to define what's called the imaginary unit. Okay, the imaginary unit is the square root of -1, and we call that I. Okay, we talked a little bit about why we need imaginary numbers in class, and there's a couple videos that I'll link for you in case you're interested. But just kind of the nuts and bolts of this to help you get started is this definition here. The square root of -1 we're going to call I. Now, the square root of negative numbers doesn't really make sense if you think about, in terms of real numbers. If you think about something like the square root of -9, right, we can't really do that. We know that 3 squared is +9, and -3 squared is also +9. So what number can we square to get -9? There's not a real number, and so we have to represent that some other way, and this is kind of how we do it. So this is important here. For these problems here, what we're going to do is we're going to simplify using this definition. So we're going to start by basically factoring this, and we don't have to factor it all the way down every single time, but we do want to factor out a -1. Let me show you what that looks like. In this case here, we'd have the square root of 25 times -1. We kind of factor out a -1. Now, I'm going to write this in parentheses because otherwise it looks like a -1, and we want to make sure that we know that these are getting multiplied here. So this is 25 times -1. From here, I can use one of my properties of roots, and I can say this is the same thing as the square root of 25 times the square root of -1. So our goal here is to kind of isolate that square root of -1 so that we can rewrite it as an I. Now, square root of 25 we can do, that's 5. Okay, the square root of -1, that's going to be I. We're just going to call that I. So there's not a real number answer to this, but using this definition, the imaginary unit, we can kind of simplify it and make it look a little bit nicer. All right, let's look at another one of these problems. Let's take the square root of 147. Okay, now 147 is not a perfect square. So what we might want to do here is we might want to factor this guy. So it looks like what we're going to have is a 49 and a 3. And 3 is prime. But 49 is 7 times 7. Okay, so there's our prime factorization. Now let's not forget, since this is negative, the other factor that we're going to have here is a -1. So I would rewrite this as the square root of 7 squared, 3 to the 1, and then I put in one more thing. I'm going to put a -1. Again, I'm going to put this in parentheses. I know it's kind of weird. It looks kind of weird, but we want to make sure that this doesn't look like a subtract 1. This is a multiply by -1. From here, we can, again, split this guy up into separate roots. So we have the square root of 7 squared. We have the square root of 3 to the 1, and then we have the square root of -1. So now that these are all kind of separated, this guy is going to come out to be 7, right? The square and the square root are just going to undo each other. This guy I can't really do anything about. That's the square root of 3. And then this guy is the imaginary unit I. Okay, just as a convention or as like an accepted way of writing these things, we do the number first, and then we'll do the I, and then we'll do the root at the end. Okay, so that's the answer there. These are basically just simplifying radicals. We've already done that. We know how to do that. We just have to add that extra idea of if it's a negative number that we're taking the square root of, we're not going to get a real number. We're going to get something kind of funky, and so we use I, the imaginary unit, to help us out there. All right, now these next ones, we actually did some of these in class, and you can take them kind of just right out of your notes. But these two are going to be a little bit different. So let me show you some patterns. This is a similar pattern to what we saw in class, but if you missed it or if you need it again, let me show you how this works. The powers of I are interesting because they repeat. So there's 4 regular powers of I and then some repetition. So I to the 1 is obviously just I. That's how we would write I to the 1. Okay, now keep in mind for a second that the square root of negative 1 is the definition of what I is. So when we look at I squared, what that would be is the square root of negative 1 squared, right? I is the square root of negative 1. So I squared is the square root of negative 1 squared. Notice the square root and the square are going to undo each other, and I'm going to get a negative 1 here. All right, now we get I to the third. Okay, I to the third power we can rewrite as stuff that we already know or have already defined. We can write this as I to the 1 times I squared, right? And just kind of count our way up. Now we already know that I to the 1 is I, and I squared is negative 1. So we can rewrite this as I times negative 1, or negative I. Okay, now I to the fourth. I to the fourth power we can write as I squared times I squared using our properties of exponents. And we already have defined I squared. We know that that's negative 1. So I squared times I squared will be negative 1 times negative 1, or 1. Okay, now this is where it gets kind of interesting because I to the fourth is going to be part of any other bigger power. So let me give you an example. I to the fifth, that's I to the 1 times I to the fourth. But remember, I to the fourth is just 1. So everything after the I to the fourth, I can just think of as something multiplied by 1. So right here, I to the fifth is I to the 1 times I to the fourth, or I to the 1 times 1. So I to the 1 times 1 is just equal to I. Okay, keep going. I to the sixth. That's just I squared times I to the fourth. Remember though, I to the fourth is 1. So this is I squared times 1. But that's just I squared. And we already know that I squared is negative 1. Okay, I to the seventh is equal to I to the third times I to the fourth. So again, another I to the fourth. That's just a 1, just a regular 1. So this is going to be I to the third times 1, which is just I to the third, which we already know is negative I. Okay, I to the eighth is I to the fourth times I to the fourth. Okay, I to the fourth times I to the fourth is going to be 1 times 1, because we already know I to the fourth is 1. So this is 1 times 1, and that's equal to 1. So notice the pattern here. I, negative 1, negative I, 1. I, negative 1, negative I, 1. It's going to keep repeating. I, negative 1, negative I, 1. Time after time after time. This just keeps happening over and over and over. So really the important ones to know are the first 4 here. Okay. Now we might want to rewrite these just like a little bit more clear so we can see. So we have I to the 1 equals I to the 2 is negative 1, I to the 3 equals negative I, and I to the fourth equals positive 1. Those are the only 4 options you're going to get for a power of I. It just keeps repeating. Now because it keeps repeating every time, or every fourth number, what we can do is we can divide by 4 to see how many times it goes through this cycle. Okay, so let me kind of explain how that's going to work with this guy. Okay, if I do 14 and I divide it by 4, what's happening here is I'm trying to see how many times it cycled through, right? Because there's 4 different options here, and so I divide by 4 to see how many times it went through this cycle. So when you simplify this, you're going to get 3 and 2/4, but what we want is like 3 remainder 2, okay? So what this means is it cycled through this pattern 3 times, and then remainder 2 is going to end right here on I squared. So if I have a remainder 1, I'm going to get I. If I have a remainder 2, I'm going to get negative 1. That's the same as I squared. If I have a remainder 3, that's the same thing as I to the third. That's going to be negative I. And if I have a remainder 0, because you can't have a remainder 4 when you're dividing by 4. If you have a remainder 0, that's going to give you a 1. So when you look back here, you're like, okay, this is 3 remainder 2. That means I go through this cycle 3 full times, and then I go 1, 2, and I end up here. So I to the 14th is the same thing as I squared, which is negative 1. Okay? Another way to think of it, if you want to, is this is I to the 4th times I to the 4th times I to the 4th times I squared. Right? 4 plus 4 plus 4 plus 2, that's 14. But all these I to the 4th, that's just a 1 and a 1 and a 1. So really this is just I squared. And I squared we know is already is negative 1. Okay? Same thing is true on this guy for 23. So I to the 23rd, we got, if we do 23 divided by 4, we're going to get 5 remainder 3. Now, it's been a while since we've used remainders because we usually write those as fractions, but it's helpful in this case. What this means is that when I get I to the 23rd, I'm cycling through this pattern of 4, 5 different times, and then I have a remainder 3. So, boop, 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 right, 1, 2, 3. So this is actually going to be the same thing as I to the third, which is negative I. Okay. Now, kind of crazy, but if you think about it, if you want to write it this way, you can. We just want to use all the I to the 4ths possible. So I to the 4th times 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 I to the 3rd. Sorry, that's a little messy, but we got 4 plus 4 is 8, plus another 4 is 12, plus another 4 is 16, plus another 4 is 20, plus 3 is 23. So this is how I can write I to the 23rd. But remember, all these I to the 4ths, those are just 1s. Okay, so we just get I to the 3rd. That's what this divide by 4 means. It's how many groups of 4 can you pull out. That's how many times you cycle through this pattern. Whatever your remainder is, that tells you where you land. So remainder 1 is I to the 1. Remainder 2 is I squared. Remainder 3 is I to the 3rd. Remainder 4 is I to the 4th because you have no remainder, which means 4 went in perfectly. It went in an exact number of times. Okay, so that actually gets you several of these problems. Okay, now in these guys here, we have multiplying these like imaginary numbers. So we kind of treat I like a variable, but we kind of simplify it at the end. So if I was a variable, I would say that this is the same thing as 5 times 6 times I, using my commutative property of multiplication. So this would be a 30I squared. Okay, so that's just no different than a variable. The only difference now is at the end, once we have that, we remember that I squared is actually negative 1. And so we write this as 30 times negative 1, or negative 30. So I isn't really a variable in the sense that it represents an unknown. It's kind of a variable in the sense that it represents a known that we want to not really deal with. So we kind of use it like a variable. Okay, so here, this is negative 9 times I squared, which is negative 9 times negative 1. So you can figure out what's going to happen with that guy. Okay, 15 and 16 are going to be really similar to those problems, so I'll let you do those. Okay, 17, we have these like polynomials basically. 17, 18, 19, 20, 21, 22. These are all like kind of polynomials. And something kind of interesting happens with these polynomials. In this case here, what we want to do in these three cases is we want to FOIL because we have two binomials. So if we look at this guy right here and we FOIL it, we're going to get first terms, x times x, that's x squared. Okay, outside, that's x times negative 5i. This is kind of weird, but this is going to be negative 5ix. Okay, then we have the inside terms. Those are these two guys. That's going to be positive 5ix. Okay, and then the last terms, these two guys, we're going to get 5 times negative 5, that's a negative 25, and then I times I is I squared. So the negative 5ix and the 5ix, those are like the same thing, but opposite signs. They're additive inverses, so those are going to cancel. Okay, so I have x squared. Now, negative 25i squared is negative 25 times negative 1, because remember, I squared is negative 1. So this negative 25 times this negative 1 gives me a positive 25. Okay, now try this one and try this one. That's going to help you practice and see what happens. But the idea here is that these are conjugates, right? These are conjugates as well. You have the same terms, but one's negative and one's positive. What's going to happen with conjugates is you're going to get that middle term canceling, and then you're going to get something over here. This conjugate pair here with these imaginaries gave us a sum of squares. These conjugate pairs should also give you a sum of squares. And we're going to use that later on in this assignment. All right, now I didn't have a whole lot of time to cover one of these in class, so let me help you set that one up. This is a trinomial times a trinomial. So what I would do for these guys is I would set up a 3x3 box. We're going to use the box method here. We've never done a 3x3, but this actually comes out pretty nice. Okay, so onto the left of the box, I'm going to put x, negative 3, and 2i. Those are the three terms from this trinomial. And then for the other trinomial, I'm going to have x, negative 3, and then positive 2i. All right, so just like we did last time, or before when we did this, what's inside the box comes from multiplying what's outside. So x times x is x squared. X times negative 3 is negative 3x. And then I have x times 2i. So this is going to be 2ix. All right, then we have negative 3 times x, which is negative 3x. We have negative 3 times negative 3, which is positive 9. And then I have negative 3 times 2i, which is negative 6i. Okay, bottom row, 2i times x will be 2ix. 2i times negative 3 is negative 6i. Sorry, hold on. I think I messed something up here. Oh, shucks. Okay, sorry. I put, that's okay. We're going to keep going the way it is. This is supposed to work out a little bit nicer, but that's okay. I should have changed this to one of these to be a minus, but that's okay. This box is going to be a negative 6i, and then this last box here is going to become a 4i squared. Okay, so some of these things will simplify. Some of these things are like terms that we can combine. We got a 2ix. Okay, so what we got is we got an x squared. Okay, we got a negative 3x and a negative 3x. That's going to be a negative 6x together. Okay, and then we got some ix's. So we're going to have plus 4ix. Okay, and then we're going to have some i's. That's going to be negative 12i when I combine these two guys. And then I'm going to have a plus 9. And then this is interesting because, remember, I squared is negative 1. So this box is really 4 times negative 1, or negative 4. So what I get is x squared minus 6x plus 4ix minus 12i plus 5. Okay, now that's kind of brutal. That actually, I mean, that's what it comes out to be, but this was actually kind of a mistake because I kind of did a bad problem here. And I'd made the same dang mistake on number 21. So, sorry about that. This will work out better if one of these is a plus. That's my mistake. I forgot to make one of these a plus. So, 22 is probably the better one to do. So, let's do that one together. And don't worry about 21, or you can kind of scrap that one. That, again, that's like kind of a typo. That's my bad. But this one, 22, is actually what I want to show you. 22 is a better problem. Okay. All right, so I got x, I got 9, I got negative 4i, and then I got x, and I got 9, and I got positive 4i. That's really what it's supposed to be. That was how I was supposed to set this up. Now, in this case, we're going to see a lot of stuff cancel, which will be a little bit nicer. Okay, so we got x squared, we got a 9x, and we got a 4ix in the top box, just multiplying the outsides here. Okay, then I got a 9x, an 81, and then a 36i. Okay, down here in the bottom, I got a negative 4ix, I got a negative 36i, and then I got a negative 16i squared. Okay, so now this is this was actually supposed to happen. The 4ix and the negative 4ix cancel each other. The negative 36i and the positive 36i cancel each other. These don't cancel because they're both positive, but they combine. X squared plus 18x. Okay, and then I got this 81 and this guy, negative 16i squared. But remember, I squared is negative 1. So this is actually negative 16 times negative 1, or positive 16. So I'm going to cross that out and put a positive 16 here as a replacement. So I got my x squared, I got my 18x, I got my 81 plus my 16, and those together are going to give me a 97. This is what I was trying to plan these guys to come out as. That's just a silly typo. But sometimes the point that I'm trying to show you here is that sometimes you multiply two polynomials that have like some imaginary numbers in them, and you get a full real polynomial, a real quadratic in this case. And so that's kind of an important discovery to make. So on 21, here's some things you can do. You can either just kind of do it the whole way. Of course, there's like, the typo that should have been, this should have been a plus. If you do this as a plus, then this will actually work out to something more like this, which is what I meant to do. So sorry about that. Okay, now we got factoring. In order to factor these, we just have to have some intuition about multiplying. So when you go back to these problems here, 17, 18, and 19, what you should see is you should see 3 different sums of squares. When we have these conjugate pairs that have i's in them, instead of getting a difference of squares, we get a sum of squares, because these I squareds that we get at the end change the sign of that last guy from negative to positive. And that's pretty much what we have here. So the trick to these problems is just inductive reasoning. It's basically understanding how the multiplication works so that you can reverse it. So when I have this conjugate pair with a plus 5i and a minus 5i, I get x squared plus 25. And we know 5 is the square root of 25. So if I have something like this, k squared plus 4, I know the square root of 4 is equal to 2. And since this is a sum of squares, then it should probably factor to k plus 2i and k minus 2i. Okay, now if you were to double check, you'd get k squared, we're foiling here, k squared, minus 2ik plus 2ik, which cancel, and then at the end you get a negative 4i squared. But negative 4i squared is negative 4 times negative 1, or positive 4. So yeah, this comes out to k squared plus 4. So we're just factoring here, which is the opposite of multiplying. Okay? We want to recognize the pattern from 17, 18, and 19, and then apply that pattern to 23, 24, 25, and 26. Recognize that these are all sums of squares, and those come from conjugate pairs that have i's in them. Okay, that's how that one works. All right, these last ones are just kind of like grab bag problems. They're just kind of some, just kind of testing your ability to multiply and to understand powers of I. So these two, you're going to get a negative 42i squared, and you know what I squared is equal to negative 1. This one here, you have 3 different ones. So let's look at this one. Okay, so 7 times negative 5 times negative 2, just the number parts. Well, negative 5 times negative 2 is 10, and 10 times 7 is 70. So the number parts give me a 70. Then I have I times I, which is I to the third power. So we go back to our table, we look at what I to the third power was, and we know that that's negative I. So this is actually 70 times negative I, or negative 70I. Right, so when we multiply things that have i's in them, we get powers of I. But remember on the previous page, we talked about how to like simplify powers of I. There's really only 4 options. There's I, negative 1, negative I, and then positive 1. So here what you need to do is you need to do a power of a product here. This 3 should apply to the 4 and to the I. Okay, then you can simplify 4 to the third, and then you know what I to the third is based on what we did in the previous page. Here you're just going to FOIL. I times 4, I times 5I. But once you get that power of I, you need to simplify and make it into one of those 4 things. So again, here were the powers of I to the 1 is I squared is negative 1, I to the third is negative I, and I to the fourth is I. Okay. So that's a quick run through. That should get you started. In fact, that should get you a lot of the way through there. We did several of those problems. The only kind of weird thing was these 3, so sorry about that. That was my bad. What you could do if you wanted to is you could try this problem number 20. What it was supposed to say was x minus 3 plus 2i and then x minus 3 minus 2i. Okay, so with what I actually gave you, this is the answer. But if you do this problem instead with a plus and a minus, you're actually going to get a trinomial, a quadratic trinomial. And again, if you change this negative to a positive, and make sure you have a negative and a positive, you should also get a quadratic trinomial. These should both be plus 5, but you should have a minus 6i and a positive 6i. So if you want to give that another try, go for it. That will be a good exercise for you. And yeah, thanks for watching. I'll see you guys back in class hopefully soon.